So my wife often tells me that I do things backwards. And I'm going to talk today about imaging backwards with the idea of, instead of imaging with the main lobe of a beam, can we image with the nulls in a beam? So if we think about beamforming and in terms of images, we know that the presence of sidelobes can distort image features and reduce image quality. And so we use apodization, right, to reduce side lobe levels with tapered windows. But of course, this typically comes at the expense of broadening the main lobe and a loss in lateral resolution. So there have been a lot of different apodization techniques to try and reduce side lobes while maintaining lateral resolution. In radar, there's this technique, sum difference technique. And what they do in radars in this particular technique is that if they want to maybe separate two small targets close to each other, they might use the null of a beam instead of the actual main lobes of the beam to do that, because the nulls, if you look at a null in a beam pattern, they fall off a lot more sharply than the actual beam rolls off. And so they'll pass the radar across the two objects, pass the null across the objects, and then subtract off from a main beam, and they're able to better resolve these targets. So in this particular work, we just wanted to try and adapt that particular technique to see if we could use this for ultrasound imaging and improving maybe some lateral resolution and other things by imaging with the nulls. And we call this technique Null Subtraction Imaging. And hopefully it'll reduce side lobes, but at the same time, give us a boost in that lateral resolution. And maybe for particular tasks, it might be useful. For others in diagnostics, it might not. So we're just going to examine a few of those today. And the technique works by considering how you would place a null at the broadside. And we know that the beam pattern is related to the Fourier transform of the product of the aperture function times the apodization function. So if we have an apodization function that looks something like this, say we've got 32 elements, and we have a rect function on one side and a negative rect on the other side, you have a zero mean, then we know that the Fourier transform of that, or the beam pattern that results from that, we'll place a null right here at the broadside. And as you look at this null, you see how sharply it declines and then spreads back out compared to how the beam, just kind of falls off in its natural diffraction pattern. So we're going to create our images by first, we'll receive all the stuff on our channels, our channel data, and we'll apply the apodization. All this is going to be done on just receive only. We'll apply first an apodization which is zero mean, like the one you see here. Next, what we do is apply a second apodization, and that second apodization is very much like the first one, except we apply a small DC bias to the zero mean weighted apodization. And what that does is it actually matches the main lobe and the side lobes pretty well, as you can see here, but most of the energy goes into bridging the null at that particular point. So what we're going to do is create an image with the null, create an image with this bridged part here, and actually one more thing. We're actually going to create a third apodization, which is just the flipped apodization of the second apodization. That kind of balances the energy on both sides of the null. So we'll create a couple of images. We're going to do this with the envelope data. We'll create the images from the two non-zero mean apodizations, sum those together, and then we subtract off the zero mean null beam. And what you get is just that bridged part in the middle is what is left over. And you can see from, this is our NSI beam here. This is just a simple simulation of what that looks like in field 2. You have rectangular apodization on an array here with 32 elements. And you've got your side lobe here about minus 13 dB or 15 dB or whatever that is. And over here in the red, you have the NSI beam. And it has certain characteristics. Obviously, the side lobes are pretty low because we're able to cancel those out really well. But it has an odd beam shape, very conical, a very pointy beam shape at the top. And if you look at the minus 3 dB width here, because we're just doing this on receive, it's much narrower than what you would get with your conventional beam, which is diffraction limited. So we're going to look at a few experiments. We're going to look at experiments mainly today to show how this particular technique performs under a series of different imaging tasks. What we use is just a simple Sonix RP with a SonixDAQ with apodization on receive only. We use an L94 array, 5 megahertz. It's got 128 elements, but we broke it into sub-apertures of 32 elements to create our images. We did our experiments with some wire targets, and then with an ATS-539 phantom, which contains wire targets, anechoic targets, and hyperechoic targets, so we could look at the different imaging tasks. Also, it turns out because the beamwidth that we get from the NSI is very, very narrow, in order to properly quantify it, we had to kind of fill in the in-between spaces. So you think about each line being a pitch apart, and the pitch for this particular array was about 300 microns. And that wasn't sufficient for us to be able to actually characterize the beam properties of our NSI beam. So we actually took our array, we had it stepped at every 5 microns to fill in the extra space in between so we could better quantify these beam properties. So not very practical in terms of medical imaging, but it's what we had to do to characterize it initially. And here are the wire targets in the ATS phantom. On the left, of course, you have the rectangular apodization. On the right, you have the NSI, using, again, those kind of square wave apodizations. You could use some sort of tapered apodizations as well, and we've done that, but for today, I'm just going to show you the rectangular ones. So what you see is, of course, at different depths here, and we focus at each depth so that the 3 dB beam width, if we characterize that, would be approximately equal to lambda times the F number, so it's a nice round figure to report. And you can see from the rectangular apodization, compared to this, and you've got little bright spots right in the middle of that, that you get a much narrower beam with the NSI here. You also get some funny things happening with the speckle, which will affect some other diagnostic tasks a little bit later on. Specifically, what happens is you take the bright spots of the speckle, you kind of push them up, and the dark spots you kind of bring down, which causes a variance in your speckle to be much larger, which is going to affect contrast ability later on. But if we just look by the numbers here, look at the minus 3 dB beam width in millimeters or in terms of wavelength for the rectangular, you're looking at wavelengths here, it's approximately the F number, so 1 wavelength, 2 wavelengths, 3.29 wavelengths. Here at 4, we get 5. If you look at the NSI beam width, we're getting a factor of 5 to 6 on each one of these depths. So we're really improving that lateral resolution. We've got lower side lobe levels. We've measured the main lobe to side lobe ratio from those images. And we get about a 10, 11 dB drop in those side lobes. And this is with rectangular type apodizations. So we've improved the lateral resolution for these wire targets, improved the side lobes, and we think that's pretty awesome. These images, by the way, were made with the 50 dB dynamic range. We also just wanted to look at 2 wire targets in the water, just to show that we could separate them out, whereas with conventional rectangular apodizations over here on the left, you see it's just a blob. But here you see those clearly separated. And in order to show a nicer image, this is just a 30 dB dynamic range. But I think it shows clearly the lateral resolution and gains that you get, which you would expect with this kind of a technique. So let's move on to some other imaging tasks. Specifically, let's look at some anechoic targets. So on the left here, you've got the anechoic targets here, and I'm going to basically look at the CNR for this one here. You get a minus 2.24, and that's with your conventional imaging using the rectangular apodization. When we use this NSI, you see what happens to the image. I think the technical term is we crap out the image, right? So you see the speckles very bright, and then you have these dark mottled spots here, and it's harder to actually make out these particular anechoic targets. So it's not very good at showing the contrast there. But we did something really just simple, something naive. We just took the rectangular image here, the conventional image here with our NSI image, and just averaged the two together. And when we did that, what we got was an improvement actually in the CNR in this particular image here. It should be more clearly able to spot these particular images compared to this image over here, these anechoic targets, even the smaller ones where you've got less stuff in the middle. And you've got a little bit better resolution too. We sacrifice some of that lateral resolution, so if we do the wire targets and do the same thing, we sacrifice about half the resolution gain that we get, but we still have a resolution boost. And in terms of the anechoic targets, we actually get, according to the CNR metric, a bit better performance. That should say hyperechoic target. So we look at hyperechoic targets. Here's the rectangular apodization. Here's our NSI again. And again, And you've got this large variance in your speckle. The mean values may be the same, but it's more difficult to make this out. We've lost contrast pretty significantly using the NSI technique. We do the naive compounding where we just average the two together again, and we get some of that back, but still not as good as what we would get with just your conventional technique. So, there are some diagnostic tests that maybe this NSI works well for, and others that maybe more work needs to be done, right? Here's one simulation, though, I do want to report, because it's hard to necessarily control the amount of electronic noise in the system. We just wondered, well, what happens when we have noise in the system? So we just put noise on the channels. We did some beamforming in simulation. We have a noiseless case with the black line, 35 dB of the red, and then 10 dB SNR for the blue line. And with rectangular apodization, of course, you get your beam and you get some noise out there in the side lobes. For the NSI, though, you actually suppress some of that noise. And the reason why is because we're taking our apodizations, and they're pretty similar to each other except for that bridging across the nulls. A lot of the energy in the signal is in the main lobes, which is where the noise is. So when you're subtracting one from the other, you're actually subtracting highly correlated noise, and you're reducing the noise in the system. So you're actually getting a bit of a boost in the signal to noise using this technique. At least that's what the simulations show. So let me conclude here. There's some good. This NSI technique was capable of producing some dramatic improvements in lateral resolutions up to a factor of 6 with corresponding decreases in side lobe levels and boost SNR. So this could be useful for detecting things like microcalcs or some other particular applications where it might be useful. The bad, so the good, the bad, and the trade-off here, the bad is that we dramatically affect the speckle due to the nonlinear processing of these images, because we're adding and subtracting envelope-based images, right? And this, of course, resulted in decreases in the CNR for both the anechoic and hyperechoic targets, so that you were not able to detect them nearly as well using this technique. The trade-off is, though, that we can compound with your conventional image, retain some of that lateral resolution boost and the side lobe boost, and for the most part, retrieve the contrast, the CNR, but again, at the cost of some spatial resolution. So lots of things that we can still try. We've got a lot of ideas in mind. I'm just listing a few here. Maybe some looking more at tapered apodizations to further improve contrast. Plane wave compounding, because everyone does that, right? Got to add that to the whole mix. Other techniques to help improve the spectral characteristics, and obviously this is far from optimized at this point. I will throw one last little image here, because we just got it this past week, where we did minus 10 to 10 degrees with plane wave compounding, and at 21 different angles. And as you can see, we actually retain our lateral resolution with this image, and we get, and we get a pretty good CNR. It's not what it was with the rectangular, but using plane wave compounding, we actually reduced these funky speckle artifacts a lot. So hopefully we'll come up with ways to improve the speckle artifacts, retain the lateral resolution and side lobe boosts, and maybe this can be useful in the future. Anyway, that's the end of my talk. Thanks.